Okay, guys, we're going to continue with 2.3 using scientific measurements. Now, accuracy and precision. Accuracy is the closeness of a measurement to the correct or accepted value. Accuracy is getting it right. Precision is the closeness of a set of measurements. This means you're getting around the same answer every time. An example of this, we see the first where they're aiming for the bullseye and every single dart misses. And all the darts aren't in the same place. So, very low accuracy, very low precision. Here, all the darts missed the bullseye, so they didn't get the right answer. So it's very low accuracy. But they're all in the same place, so they have a very high precision. I don't like this one. You really can't be accurate without being precise, because if you're accurate without being precise, that means you just got lucky. Now, in the last one, we see that all the arrows are in the bullseye, and they're all in the same place, so very high accuracy, very high precision. Now, percent error. The equation for percent error is measured minus accepted, all over accepted, times 100. And guys, you can just do the absolute value of this to keep it positive. Now, you can either have a positive or a negative number if you don't use the absolute value. Either way, it's okay. You'll get the same number. Now, with this, measured means your experimental value. It's what you get in the lab. Your accepted is your known value for it. It's the right answer, what you should have gotten. So what percent error does is percent error gives us an idea of how well we did a lab. An example of this, when we measure density from the lab experiment, it is 1.40 grams per milliliter. The correct density is 1.36 grams per milliliter. And it wants to know, find the percent error. So the percent error equals our measured amount minus our accepted amount divided by our accepted amount times 100. Now we take this, and what we'll have is we'll plug it in. We'll have 1.40 minus 1.36 all over 1.36. And guys, remember this is grams per milliliter. We got to put our units, because without units, numbers are worthless. But what we'll see is as we work this out, we will get a percent error of right around 2.5%. Okay? Anything below, or not 2.5, 2.94. I'm sorry. Anything below 10%, you did a very good job on the lab. Okay? Now, significant figures. Significant figures are in chemistry because we have to use the least precise instrumentation. Okay? If we're doing a couple different instruments to measure something, we can only use the least precise amount, because if not, we're just going to compound errors. So for example of this graduated cylinder is measured out in tens of milliliters. So you have 10, 20, 30, 40, 50, 60. We know we definitely have 60 for sure. We're not quite to 70, but we can't say for certain if it's 61, 62, 63, 64. So we'll take a guess, and we'll just say 64 milliliters. Now, on this other graduated cylinder, we see that it's broken up not just into milliliters, but those lines represent tens of milliliters. So we have a tenth of a milliliter. So we know for sure as we move up those lines that we at least have a tenth of a milliliter. We get to a point where it's kind of in between a line, and we take a guess. Remember, always one digit more than what you're certain. Now, to determine the significant figures, we have to use these rules. Okay? All non-zero numbers are significant figures. So 1, 2, 3, 4, 5, 6, 7, 8, or 9. Those are always significant. Now, zeros depend on the location of the number. If they're leading zeros, we never count them. If they're embedded zeros, always count those. Leading zeros would be numbers in front of a non-zero digit. Embedded zeros are like a sandwich. Example of that, 505. That's sandwiched in between each other. So it's embedded, it counts. And then we have trailing zeros. And those only count if there's a decimal. So, example of this, in 5,000, those zeros wouldn't count. But in 0.50, this zero at the very end is a trailing zero after a decimal, so it would count. Now, rounding. When rounding, we need to use to write these calculations with significant figures. Now, calculators give us a ton of numbers. So, when we round, if it's 5 or above, we always round the next number up. If it's less than 5, we keep the number the same. An example of this, we see here, we're going to make the following have 3 significant figures. See, we have 1, 2, 3, 4, 5 significant figures here. We can only have 3. So, that 5, we'll round that 1 up to 762. Here we have 5 again. Well, we can only have 3. 1, 2, 3. That 3, since it's below 5, doesn't round it up. Here we have 4, so we go the first 3. 1, 2, 3. And that doesn't round that up, so it's just 1.4. And again, we keep going. This number has 5. We can only have the first 3. So that 8 rounds that 7 up. Now, when calculating using significant figures, if we're adding or subtracting, we always end with the least number of decimal places. So we see in our first number, it goes all the way out to the hundredths place. In our second number, it goes to the tenths place. In our third number, it goes to the thousandths place. Since the 3,536.2 only went to the tenths place, we round everything to the tenths place. Another example of this, we see here we're subtracting. 4.8 goes to the tenths, and 3.965 goes to the thousandths. So the smallest is to the tenth, so we have to round it right there, and that 3 doesn't round it up, so it's just 0.8. Now with multiplying and dividing, we always end with the least number of significant figures. So we look at our factors being multiplied, and we see we have 3 significant figures, 3 significant figures, and 2 significant figures. Least amount is 2, so we have to round our final answer. This is what we would get in the calculator. We have 1, 2, 3, 4, 5, 6. Can't have 6, have to have 2. So it either be 500 or 5.0 times 10 to the second, if we put it in scientific notation. Another example of this, we have 278, which has 3 significant figures, and 11.70, which has 4. So we round our answer to 3, which we see we have 23.8, which is 3 significant figures. Okay, guys, we're going to continue talking about measurements, and we're going to talk a little bit about scientific notation. The reason why we have scientific notation is to take incredibly large numbers or small numbers and condense them down to a workable form. Now, the basic form of scientific notation is this right here. It's that m times n raised to the nth. Now, m and n are numbers. M must be greater than or equal to 1 and must be less than 10. And n must be a whole number, and it can be positive or negative. Okay? Now, how we get m? We find m by moving the decimal point over in the original number to the left or right so that the only non-zero number is to the left of the decimal. So we look here with 56 million, and we see that we've moved it over 1, 2, 3, 4, 5, 6, 7 places to get 5.6. Okay? Here we have a very small number, and we move it over to 1, 2, 3, 4 places to get 3.099. Okay? Now, after we move them over, we look and we have to find n. So on the very first part, since we moved it over 7 places to the left, it'll be 5.6 times 10 to the 7th. And on the second number, since we moved it to the right 4 places, it's going to be 3.099 times 10 to the negative fourth. Now, adding and subtracting with scientific notation, the best thing I can say to do this, guys, plug it in your calculators. You can try to do it by hand, but sometimes it gets confusing. But just plug it in your calculator and you should be good. And that's the same thing with multiplying and with dividing. Use your calculator, guys.